Let's start with, for instance, momentum equals mass times velocity. We can do the derivative of how momentum is changing with respect to time, and then we have this is going to be the change of mv with respect to time. We can state, for instance, this is mass times the change of velocity due to time plus velocity times the change in mass due to time. Now let's suppose, or let's state that mass is not changing in time. So this is going to be to zero. I mean, could you imagine some statement where mass is changing? Let's suppose that this does not change into time. So the change of momentum with respect to time is going to be equal to mass times the change in velocity due to time, which is the acceleration. Wait a second. That is going to be force, right? So the sum of forces, which is mass times acceleration, is as well the change in momentum due to time. This is, of course, if there is no change in mass with respect to time, right? So sum of forces, or the force applied, is going to be equal to a change in momentum due to time. So, wait. According to the definition of second Newton's law, there is going to be a force if there is a change in the state of motion due to time, right? So it complies. Force is going to be equal to a change in momentum due to time. Okay, that sounds fair. Now, imagine that we pass this guy upwards. What is going to happen? Force times dt is going to be equal to dp. We can change this by integrating, and the integral of force dt, as a previous explanation, is going to be the impulse. And this is going to be, for instance, final momentum minus initial momentum. Do you remember that we said that these two were related? Well, this is the relationship. Impulse is a change in momentum. So, for instance, force times an interval of time, if the force is constant, of course, which we will be using right now, is going to be equal to mass final velocity minus mass initial velocity. And of course, these are vectors. So this is the relationship between impulse and linear momentum.